Hello everyone, this is the fourth lecture of this week. In the last class, we derived the stiffness matrix for beam element, and then today we will see how to derive the stiffness, how to derive the load vectors for beam element, and then subsequently solve a problem with the finite element method. Okay. So, if you recall, that was these are the shape functions of a beam element. If you have a beam element like this, beam element, any arbitrary beam element, and then if the corresponding, if the degrees of freedom are vertical translation is this, if we take a beam element like this, and these are the corresponding degrees of freedom, and then so this is 1, 2, 3, 4. And then shape function associated with all these degrees of freedom 1, 2, 3, 4 are these that we derive in the last class. Okay. Then we also know that the stiffness matrix, the general form of stiffness matrix, element stiffness matrix rather, that is equal to integration over the entire domain. That depends on what kind of object you have, whether it is integration over the volume or area or line, it depends on what kind of elements we are talking about. So, this is B transpose D and B, right, and d omega. And how we derive this equation? We derive by minimizing the strain energy, right. Now, so here B is the strain displacement relation and D is the constitutive relation, which tells you how the stresses are related to strain. And I asked you to please draw these shape functions and then see how these shape functions and also to understand what are the properties of these shape functions. Okay, great. Now, let us find out what is the, suppose if we consider a beam like this and it is subjected to say uniformly distributed load, load like this. So, in order to solve this is the stiffness matrix. Along with the stiffness matrix, we have to find out the load vector, and in matrix method we know how to do that. Let us see how to do that in finite element formulation. Okay. Now, before that, there are two kinds of load that an object can have. Okay. One is the body force. Body force is one example of body force is say gravity. So, suppose if you have a beam like this, a beam, and then the self weight of the beam is essentially the body force. Okay. And suppose that is represented by xb. Okay. So, xb essentially is a vector. So, it tells you in which direction the body force is acting. For instance, in this case, if we take only the gravity, then xb will be acting downward, and this value will be rho g. So, this is minus rho g, this is 0, this is 0. So, this is xb in 3-dimensional case. So, it depends on the what body force you have. Now, in addition to the body force, there is another force which is called surface force. Surface force essentially, for instance, if this beam has a load like this, uniformly distributed or varying load, it is acting on the surface. Okay, or acting when I say surface, it is essentially acting on the boundary of this domain. So, this is called surface load. So, similarly, surface load, surface force is also suppose represented as S, and this is also a vector. Okay, it gives you surface force in which direction. Okay, or traction in which direction. Now, what we want to find out is, we know that for at the element level, the Ke is equal to Ke into say dE. dE is the displacement associated for the particular element, the degrees of freedom for a particular element, that should be equal to Fe. F is the element load vector, okay, is for that particular element. So, we have already seen how to do this, how to express this. This is the expression for this. dE essentially are the unknown, so we do not have to bother that right now. We will now see how to express this. Now, in order to do that, we have to go back to the same the starting point, how we derived this expression. We follow the same approach to derive the expression for Fe. Let us do that. So, if you recall what was our approach, you see, I suppose if you our approach was we use UE. U was the strain energy. Suppose UE is the strain energy associated with a particular element. Okay, so UE. So we minimize. So we minimize UE. Let us forget about U. So we minimize U, right? The U can be written as and after minimizing U means differentiating the strain energy with respect to displacement, we get force, and that from that step we got that expression for stiffness matrix. Now, suppose a body is, there is some load acting on a body. So, if there is some load acting on a body, then that load is some work is done by that load. And what is that load? Suppose that is WP, that is W. Okay. So, W will be what? W will be, it is the work done by the surface load, and as well as it is the work done by the body force, right. So, what would be the contribution of the body force? Contribution of the body force will be, since it is acting on the volume of the body, let us let us write the it is acting on the entire domain omega, and then the xb is the, suppose displacement is d multiplied by the force is xb, okay, and then it is integrated over the entire omega. That is the contribution from the body force, right. Now, similarly, we have a contribution from the surface load, but the surface load is acting on the boundary of this boundary of the domain. So, that integration will be, has to be over the boundary, not on the domain. For instance, if you have a 3D object, then the first is integration over the volume and the second is integration over the surface. Okay. So, this will be again d, and then this is multiplied by xs. Xs is the corresponding displacement, okay, corresponding body force, and this is integration over, say, ds or d del omega, right. Okay. Now, this, in order to be consistent, this will be transposed, so that this becomes a scalar. So, this is the expression for the work done. Now, what we know is, we know that pi is equal to the potential energy. The potential energy is equal to the strain energy minus W. Okay. Now, while considering the, now before that, so d is equal to what? D is equal to this vector is equal to, you have a component in x direction, component in y direction, and component in z direction. Let us use, okay, fine. Now, then, so when we minimize it, when we minimize this pi with respect to the displacement, okay, then we, from this term, the del W del D term, we get the stiffness matrix. Then we have, so if I differentiate with respect to, say, del pi del D, so this will give you del U del D minus del W del D. Okay. So, this gave us the integration B transpose d B, right, which was the stiffness matrix d omega. This was the stiffness matrix, and that has to be equal to 0. That has to be equal to 0. Now, so for the minimum potential energy, so this gives us the stiffness matrix, and this part will give us the load vector. Let us see what is, now if we, now this has two components, one component is this, another component is this, another component is this. Now, you recall that how these displacements are expressed. Displacements are expressed using like this. If you recall that if we have suppose if d for any element, for element d, this is expressed as the ni di, right. n1 d1 plus n1 d2 and so on through the shape function. So, naturally, so this displacement, this vector we can write as like this. If d is equal to, so this vector, this is equal to, we can have a displacement which is at the element level, displacement at the say element level, and then we have a matrix for n, okay, that is transpose. So, this is how, so this d e essentially is the nodal values of the displacement, right. So, if I substitute that here in this expression, so what we get? We get that we get two term. One term will be, so let us consider only this part separately. So, this one term will be let us write it here. So, del w or del, first let us write w. W will be what? W will be integration of omega, and then this is d e, and then n transpose, which is only for this displacement part, and then we have x b, and then integration over the entire domain, and then plus we have integration only on the boundary, and this displacement is written as d e, and then n transpose, and then we have x s, and then d del omega. Okay, this is we have. Now, if we this is for w. Now, if we differentiate it with respect to del d, then what will happen? Then we have, if we differentiate it with w, then we have del w del d will be integration over the domain, then we have n transpose, the d term will go, and x b, which is the body force term, and then d omega, and then plus integration over the boundary, then n transpose, and then x the boundary term, right, and then d del omega. Okay. Now, this is we have, right. So, this is, so we have then del u del d minus del w del d, that is equal to 0. So, this is the stiffness matrix, as we have already seen, this is the stiffness matrix. This part will gives us what? This part will gives us k into d e, and this part will give us load vector. We can take it out, take it other side, and this load vector will be f e, and this f e is this integration of n transpose, or this f e is two part. One is f, this f e has two parts, say f e is, one is f e b body force star plus f e s, which is the surface force, surface part. Now, for a given element, so we know the shape functions, and then if we substitute the shape functions and integrate it over the domain, over the entire body, or over the in the case of beam, over the length of the beam, we get the corresponding forces. Just to give you an example, suppose consider the same example. Consider this example where you have a cantilever beam which is subjected to uniformly distributed load, and suppose the uniformly distributed load intensity is q. Okay, q0 is into, and in addition to that we have body force term, and the body force term is, suppose this is the body force term which is downward acting, which is rho g, the gravity term. So, we have to find out what is f b term and what is f s term. So, what will be f b term? F b term will be, if we, so f b will be f b e element level, that is equal to integration over the volume, and then n transpose, then rho g, and then d v. This will be this part. Now, this integration can be written as again integration if the uniform cross section is uniform. So, this can be written as integration over length 0 to L, and then n transpose rho g, and then a into dx. Okay, we can take A outside. Now, we already know what is the expression for n. These are the expression for n, right? These are the expression for n, and if we substitute that in that what is n then? If when we write n is equal to when we write n is equal to is essentially n1, n2, n3 and n4, right. Now, if we substitute this now in this expression and then integrate it over the length, we get this is equal to rho ag, and then this term will be L by 2 and then L square by 12, you can check it, and then L by 2 and then minus L square by 12. So, for this beam, this contribution will be this. Okay. So, in addition to that, we have one more contribution, that is Fs term. Then what will be Fs term? Then Fs term will be, similarly we can calculate, Fs will be Fs element level, that will be integration. Here it is acting on the, as I said, this integration will be over the surface. In this case, this integration will be over the length where on which this force is acting. So, 0 to L, and then we have n transpose and q0 and then dx, right. Now, we already know what is the expression for n0 for B element, we can substitute that, and if we substitute that, then this will be integration q0 L by 2 and then q0 L square by 12. If you recall, q0 L by 2 again and minus q0 L square by 12. Okay. Now, if you recall, in the matrix method of structural analysis, we first calculated the fixed end moments, and from the fixed end moments at every joint we satisfy the equilibrium to get the nodal load vector. And if you recall, for a uniformly distributed load, the fixed end actions were essentially this, isn't it? But here we can obtain, we do not have to bother about what is the fixed end moments and how to satisfy the equilibrium. Just by this expression, the entire thing, minimization of potential energy will give us both the stiffness term as well as the force term. Okay. So, then in this case, so what will be the total force? The total force will be Fe, total force term will be this term plus this term. Okay. Now, so for a given element, we have the we already have the stiffness part and we also have the loading part, right. Now, we have not yet discussed if there is a concentrated load, then what is to be done. We will come to that point shortly. It is for uniformly distributed load. Now, suppose if your load is not uniformly distributed, for instance, if the load is like this, so if we take a beam, if we take a beam and the load is, suppose take a cantilever beam or any beam, if the load is something like this, uniformly distributed, it is like this. Okay, this is like this. So, what is the load? This q0 is, q is equal to essentially. So, this is q0, this is q0. So, q is essentially your it is 1 minus x by L, right. Now, if q is this, then what will be Fs? Fs will be the body force, the force Fe term, the Fs term, because surface load. This is integration of, if you recall, 0 to L n transpose into x into q, but then q is a function of x. So, it has to be written as a function of x and then dx. If you substitute that function and then integrate it, we get the corresponding vector. So, we can have any orientation, we can have any arbitrary orientation of arbitrary distribution of load on the beam element, but if we know that distribution, if we know that function, we can substitute that function in this expression and get the corresponding load vector. Okay. This load vector is called consistent load vector. Okay. Now, once we have obtain the stiffness matrix at the element level and also the load vector at the element level. Next we have to do is we have to assemble these stiffness matrices. Not only the stiffness matrices, we have to assemble the nodal load vector as well, exactly the same way we assemble the stiffness matrix. Okay. But now it is just in a vector form. So, once we assemble them, what we get is we get a global stiffness matrix and the global load vector. Then we have to do partitioning, and once we do the partitioning, we with the reduced stiffness matrix, applying the with the information of boundary condition, we reduce the stiffness matrix and calculate the unknown displacement, right. Now, so let us take one example and then we have translated the entire process the way we have done it for matrix method. We have translated the entire process into a program. I am just going to show you that code, and just we take one example and then see how the various steps and the results what we get, and we compare the results with other methods. Okay. Now, so take an example of a cantilever beam subjected to, say, for instance, okay. So, first let us find out the code. So, the code is, yes, okay. So, this is the code. So, consider a problem like this. The problem we are considering is this. Okay. Take a beam, cantilever beam, then it is subjected to uniformly distributed load. We will come to the point later. Suppose the length of the beam is 3 meter. Okay. Entire length is 3 meter. Okay. Now, let us divide that beam into, say, 6 segments. So, we have just 1 point, 2, 3, 4, 5 and then 6. Recall in matrix method, you see it is a cantilever beam, we have just one support at the end. Now, in matrix method, how we discretization is an important step in both the cases. The matrix method also we discretize the entire structure, here also we have to discretize the entire structure. But when we discretize in a matrix method of structural analysis, we took the segments between the two supports as one segment, as one member. But not necessarily here in finite element method, you have to consider that as one member. That is why we do not call it member, it is an element. Even just one span of the beam, one member of the beam can be divided into several parts. For instance, it is just one beam, but it can be divided into several parts, and what is the consequence of that, we will come to that shortly. So, there are how many, suppose we start with, we give numbering like this. So, this is node number 1, this is node number 1, this is node number 2, 3, 4, 5, 6 and then 7, right, 7, and these are the elements number, corresponding elements number 1, 2, 3, 4, 5, 6. Okay. Now, what happens is, you see, so first we have to give the connectivity of nodal information. So, node coordinates are, this is the entire length is 3. So, that is equally divided into 6 parts. So, whatever length of the length of each element we can obtain. But again, not necessarily that all the elements have to be of same length. We can have elements with different lengths as well. For the demonstration purpose, let us take all the elements having same length. Okay. So, these are the elements. Now, we have element connectivity. So, this gives you the node. Let us slightly increase the font size. Yes, that's better. Why not? Yes. So, this gives the this is the node number. So, we have different nodes, and this is the element connectivity. So, node 1 is connected between node 1, element 1 is connected between node 1 and node 2. Okay. Now, then the load is here, load is Q0, it is uniformly distributed load. We have uniformly distributed load like this, and suppose this value is Q0. Okay. So, this is Q0 here. So, this is q 0. So, EI is again you can for the demonstration we are taking is 1, you can change the values of u, and even for the same element we can have, for the same member we can have different EIs. Okay. So, these are almost same as matrix method. This is the stiffness matrix, element stiffness matrix, and recall this is the nodal load vector, the consistent load vector that just now we derived. This is there is no body force here. So, there is no body force term, it is only the surface load term. Now, this is the assembling of the load vector, the assembling of the stiffness matrix, but we have to assemble the load vector as well. This is the assembling of the load vector. So, finally, once we have this, then this is the K11, this is the partitioning of the matrix that we already discussed in matrix in previous classes, and then finally, we are solving for unknown. Once we solve for unknown, then we can obtain the support reactions and so on. So, let us find out the solution of this. So, solution is this will be this. So, let us run it. So, we run it here. Forget about this blue line, because these are the red one is the actual length, actual deformation of this beam, and the blue dots you can see, these are the obtained from the finite element solution. The blue line is not important here, because blue line just those points joining by the line, but that is not the real representation of solution. The real represented solution is this is the red one is the actual solution, and the dots you can see these are the obtained. These are obtained from the analysis. Okay. Similarly, you can increase the size. Say for instance, you can increase the number of you can make 0.5 and then run it, and then we get different solution. So, you can see the solutions are close to. What is the error between these solutions, the predicted results and the actual solution? Let us not bother about right now. We will discuss the nature of the error and how to measure that error, how to represent that error, and what are the different way that we can minimize this error. Those we will discuss later in the subsequent classes. Okay. So, now, but you see the reason why you could draw the deformed shape, because even in one element, one beam, you have several such segments. It is just not in matrix method of analysis. When you solve it, we had the displacement at the nodes, displacement at the supports, right? But here just not the displacement at the support. We can divide the beam as many times with as many number of elements we want, and that every discretization we get the intermediate values of the displacement even in a single member. So, that is how we can draw the deformed shape. Okay. Now, one important point, let us see the what is the kg, what is the okay, this is the stiffness matrix of this element. Okay. Now, you see this is an interesting observation here. The stiffness matrix, you see, you recall some time back we were talking about bandedness in a stiffness matrix. All these elements in the stiffness matrix is 0. This is 0, and then this is also 0. This is 0. So, only non-zero elements in the stiffness matrix is the off diagonal term and the diagonal term and the few off diagonal terms. Okay. Now, so the advantage of having this is when you have a banded stiffness matrix, there is some of the when you actually try to solve it, at the end of the day we have to solve some system of equations, linear equations. That solution process, the operations while solving these equations are much lesser. Now, suppose you take an example of the same beam, but we discretize slightly different way. For instance, suppose this is the beam, once again you take this beam, and this is divided into 6 parts, 1, 2, 3, 4, 5, 6. these are the element number 1, element number 2, element number 3, element number 4, element 5 and element 6. Okay. Suppose the node numbers are, this node is node number 1, this node is node number 3, this node is node number 5, this is node number 7. If I give node number arbitrarily, node number 4, node number 6 and then finally node number 2, node number 2. Okay. So, here the node numbers are in a sequence in a particular order, but here we have given the node number arbitrarily. Then let us see what happens if the node numbers are like this. Okay. So, this is the node number. So, this is the different nodes, this is the different nodes and then corresponding connectivity is this. So, here element 1 is connected between 1 and 3, connected between 1 and 3, element 2 is between 3 and 4, 3 and 5, between 3 and 5, 3 is between 5 and 7, between 5 and 7 and so on. Okay. Let us solve it. So, F5, again forget about the blue lines. So, if you see the solution will be 7, it does not depend on your node number here in this case. But what is the important thing you see that is this one. Let us see what is the stiffness matrix. This is the stiffness matrix. You see, this stiffness matrix is no longer a banded stiffness matrix. This is no longer a banded stiffness matrix. You see, somewhere in some of the elements at 0 here, here some of the elements at 0, then we have some of the 0 means 0 here, some are 0 here and then some are 0 here, some are 0 here. Okay. So, this stiffness matrix is not banded. So, how you, it is just not the discretization does not just mean that you have a structure and divide it into parts. How you divide into parts, how you number them, your computation, the intensiveness of the computation, how many numerical operations that you have to perform, that significantly depends on these aspects. Okay. So, when you do this, when you write your own code, then please keep that in mind, and there are literature which tells you what is the best possible way to number elements in which order, so that you can get a banded stiffness matrix. Okay. So, this is the solution of beam. Now, you see the beam is one structural component. So, we have discussed what is the formulation for truss, what is the formulation for beam, but then next class we will see if our problem is a 2-dimensional problem. Okay, domain is a 2-dimensional domain, then what would be the formulation, what are the different kinds of elements that we have to use to discretize those 2-dimensional object. For truss and beam, the advantage of truss and beam is you directly can correlate with the matrix method that you studied in matrix method of analysis, because you did the similar thing in matrix method in your structural analysis direct stiffness matrix direct stiffness method. So, you could correlate between what you learned, what we discussed there, and these finite element formulation for truss and beam. But then next class we see what is the formulation for 2D element, and that will be probably something new that you have not yet done in your previous structural analysis courses. Now, but the essence of the steps will remain same. We get the stiffness matrix, the general form of stiffness matrix will be same, general form of the load vectors will be same, but since it is in different dimensions, our different the B matrix or the D matrix, those will be different. That exercise we will do in the next class. So, I stop here today. See you in the next class. Thank you.